Can you guys see that?
It's fantastic. Yeah.
Okay, thank you. I just wanted to say thank you for the paper trail for giving me an opportunity to present this. Like he said, my name is Ephraim Onyi Ekwueme. I'm a senior here at Notre Dame, and I work at the Hanjaya Putra Lab. The title of this research is Designing Viscoelastic Hyaluronic Acid Hydrogels to Direct Lymphatic Tube Formation. Firstly, I just want to do a quick overview of the lymphatic system. It is a group of organs, vessels, and tissues that protect you from infection. The system has three main functions. These include fluid balance, absorption, and the enhancement and facilitation of the immune system. Here are some parts of the lymphatic system. They include the bone marrow, thymus, lymph nodes, and spleen. A brief background of the project. The ECM of a variety of tissues, native tissues, such as the skin, muscle, and liver, have this nonlinear elastic behavior. That means they're neither fully fluid and neither fully solid. They have this viscoelastic behavior that allows them to adapt to things like mechanical deformation and matrix remodeling. Harnessing that viscoelasticity in the construction of biomaterials presents a route to mimic that native ECM that'll enable biophysical control of cell spreading, proliferation, and things like migration. An important property of these viscoelastic gels is stress relaxation, actually. As you can see here, as you increase the strain on the elastic materials, the stress doesn't change at all. But on the viscoelastic materials, there's a decrease in stretch as the time goes on. That increases cell spreading and proliferation. These hydrogels also enable rapid vascular morphogenesis, as you can see over here. Studies point to the impact of tuning the viscoelasticity of the native ECM with the type of cross-linking, possibly to direct the phenotype and fate of cultured cells. However, current studies on things like this, the viscoelasticity, are static, so protocols looking at these types of experiments are quite limited. Now I'll go into the design of the hydrogels. These hydrogels are designed with spatially controlled and tunable viscoelasticity. We were able to do this by a combination of supramolecular and covalent cross-linking on the HA background, as you can see here, the HA background. The HA was modified with pendant transbrookers merocyanine BM groups, as you can see here, that forms a homotenary complex with the free CB8 macrocycles. The CB8 macrocycle is like a tire with the inside cut out. We also modified HA with norbornene to open a route for covalent cross-linking. This opens a route for covalent cross-linking by difunctional thiol molecules right here through the thiol-nor reaction at the 254 nanometers of light. That's how it's induced, as you can see here. And this hydrogel can also be irradiated by 365 nanometers of light to make it a completely covalent elastic hydrogel, switching it from viscoelastic to elastic here. Here I'll go into the supramolecular interaction between HABM and CB8. Here you can see the absorbance spectra of the HABM in the presence of various molar ratios of CB8. As you can see the maximum absorbance wavelength switched from 374 nanometers is 396 nanometers as the ratio was increased all the way to 1.21. However, the decrease in absorbance when the ratio was increased to 0 to 0.48 right here, that suggests a complete formation of the homotenary complex around the expected ratio of 0.5, where the BM motifs are maximally coupled with the CB8 cavity. However, as the ratio increased from 0.5, that this increases the prevalence of the 1-to-1 CB8 BM complex, as you can see over here. That may start to favor that binary complex instead of the complex we see here as the CB8 macrocycles become in excess. This was further supported by this data. You can see that this remains normal right here, but it goes up and flatlines over at 0.8, thus favoring this binary complex you can see here. Now I'll go into the photodimerization of HABM by addition of CB8. Here's just the schematic of the photodimerization. And as you can see here, this is the HABM with the CB8. And over time, you can see a progression in the photodimerization upon increased exposure to UV irradiation. However, we also saw this without the addition of CB8, which was unexpected because other studies did not show this happening. But you can see here that we found that this CB8 molecule had a catalytic role, so it happened faster here than over here. And this frequency rheology sweep showed that in the G prime modulus before UV had a frequency dependent matter. That's how it switched. But after UV, it had the frequency independent matter, which suggests it changed to an elastic hydrogel. That's how they usually interact. Now this is a continuation of the photodimerization of HABM. Over here, this is a stress modulus. And you can see over time on this elastic hydrogel, there's no relaxation at all. But on this viscoelastic hydrogel, you can see stress relaxation over time. And here's the photo patterning over here. We did this with 200 micrometer strips and 100 micrometer strips. On the plus UV, this is where the elastic hydrogel would be because it's not masked by the photomask. And the minus UV is where the viscoelastic hydrogel would be. We were able to quantify the fluorescence intensity over here. This just showed us that we could spatially control where the viscoelastic and elastic parts of the hydrogel were. Here, I'll go into the orthogonal photo patterning of viscoelastic hydrogels. We use this as a way to show that the gel can be modified with multiple molecules. Here we use dye as a model, but in the future, we may be able to do it with biofunctional molecules, such as things like growth factors. Here you can see the schematic of the orthogonal photo patterning. And B and C, this is an HA-NOR-BM CB8 hydrogel. And you can see here, like in the previous slide, the plus UV is the covalent elastic hydrogel, and the minus UV is the viscoelastic hydrogel. And we did this with fluorescence and then rhodamine B. And this is the merge of both of these. We also did this with 200 micrometer stripes and 100 micrometer stripes. Then we used fluorescence intensity to quantify what we were seeing. This just further proves that we're able to spatially control where the viscoelastic and elastic parts of the hydrogel were. This is a continuation of that. However, in this, we use HA-NOR and HA-BM. This gel is a double network gel with CB8. And once again, the plus UV is the elastic hydrogel, and the minus UV is the viscoelastic hydrogel, just further showing that we're able to modify with multiple molecules and still have that spatial control of where the viscoelastic and elastic parts of the hydrogel were. This is the impact of the substrate viscoelasticity on the lymphatic tube formation. Over here, we have the representative images of the lymphatic endothelial cells, the LECs, and the elastic and viscoelastic hydrogels. You can see there's more tube formation over here on the viscoelastic hydrogel than the elastic hydrogel. And we were able to quantify this with the branch numbers being increased on the viscoelastic hydrogel, the branch length increased on the viscoelastic hydrogel, the nodes and the closed networks also increased on the viscoelastic hydrogel. And over here, we see these are also representative images of the LECs. And we see on these viscoelastic hydrogels, these semicircle-like branch structures that show that it supports a tendency for these closed networks to develop on these viscoelastic hydrogels, as you can see here, instead of the elastic hydrogels over here. A continuation of that, we looked at these key lymphatic markers, and on all of these, there was an upregulation on the viscoelastic hydrogel when compared to the elastic hydrogel. This suggests that the viscoelastic hydrogel support these lymphatic phenotypes and promote an upregulation of lymphatic cord-like structure formation. And you can see the significant factors here. In conclusion, we demonstrated that these dynamic hydrogels could provide spatially controlled substrates for culture of LECs to direct the lymphatic cord-like structure formation. These hydrogels enhance the expression of key lymphatic markers and promote CLS formation. And overall, these hydrogels offer a simple route to spatially control the lymphatic cord-like structure formation. And I just want to say thank you to Paper Trail. Thank you to the Hanjaya Putra Lab and my mentor, Fei Fan here. And that's all. I'll take questions now.
Yeah, thank you so much for that presentation. It looks like we have a couple of questions. I think Teresa was first. If you want to unmute and ask your question.
Hey, that was awesome, Onyi. You probably don't know anything about me, but I love light modulated materials. And so it's very cool to see light being used. I don't know a lot about the sulfur and norbornene reaction, but I had thought that was done with like 365 nanometer light. But I saw you use 254, which I think we often consider you can